Hello, happy Friday, everybody, and welcome to today's virtual panel discussion on our new TPA that we're basically delivering to the market on the 4200. This is a material that we've developed together with Evonik. And the cool thing is not only to develop with the well-known material company Evonik, but we're very focused on, as we develop materials in the future, on focusing on customers and their applications. And so this development also included working with Jesse at Go Proto and Alex at Fast Radius. And today we're going to be talking about that experience, but also the material itself, kind of what it's good for, and ultimately some of the applications that you all might be using along those lines, right? So I'm going to ask each of the panelists to introduce themselves, but first kind of process or sort of the overview of the next hour or so. So I'll start off by kind of talking about HP's perspective of this flexible polyamide, kind of the value prop, the applications that we see. At that point, I'll turn it over to Rebecca, who'll talk about Evonik's perspective and kind of their experience, kind of who they are and how they see this material. And then we'll turn it over to Jesse and Alex. I'll ask a question or two, kind of leading into what they see as their experience with the material, their experience with the application, kind of their experience with the development program, and then we'll open it up for questions. And so if you have questions as they come along, please enter it into your chat bar down below, and then as we get into that portion, I will answer them or I'll ask the questions of the panelists or whoever best that we can as we basically move ahead. So first, let me introduce myself. I'm Tim Weber. I'm based here in sunny Corvallis, Oregon. Typically starting in October to about May, it pours down rain, but we actually have a nice sunny day, which you can see behind me in my home office. I've worked for HP for about 27 years, developing technology, first for our core business, 2D printing, inkjet printers, all the way from $100 printers up to web presses that sell for 10 million. About 6 years ago, I switched over to the 3D organization. I've been with HP's 3D business since the beginning, primarily responsible for developing materials, agents, the print heads for both our plastics business, which we're talking about today, a new material, but also our metals business, which we announced a couple of years ago as well. So now I'll turn it over to each of the panelists. Let's start, Rebecca, with you.
Hi, thanks, Tim. Very excited to be here today with these great partners, HP, Go Proto, Fast Radius. So my role is business development at Evonik, and I'll tell you about Evonik in a minute, but I'm based in Atlanta, Georgia, which was sunny and nice until about a week ago, and now it's freezing cold. I work in our high performance polymer business, supporting materials into 3D printing. So what this means, I work with printer manufacturers to support materials and integration into their machines, as well as formulations and integration of our materials into their hardware. We also work with end users for pulling through our materials and supporting new effects into end use parts. I'll give it back to you, Tim.
Great, thanks, Rebecca. Hey, Jesse, why don't you introduce yourself and your company?
Thank you very much, Tim. And just like Rebecca said, I'm very excited to be here. We're excited for our continuation of our partnership with HP. We've worked together very closely since we started with multi-jet fusion in about 2017 when it came on the market. So it's been an important part of our business, which is rapid product development. Our company manufactures prototype through production, plastic and metal parts. We focus on anywhere from one printed part or machined part to some prototype sheet metal parts up through production, injection molding in a wide variety of materials. And we're excited today to talk about the TPA material because it addresses a need in the usual bill of materials on products that include elastomer parts. There has been a hole in that place where we either could 3D print parts that were not very usable, or maybe cast them in urethane, or maybe have to go into injection molding. So we're excited to talk about that today. I am the president and CEO of Go Proto. So I run both sales as well as manufacturing. So I'm very aware of both sides of customer needs and as well as factory capabilities. So part of what we can talk about today too is just how well the material works in the manufacturing environment.
Yeah, perfect. Thanks, Jesse. Alex, over to you and your company.
Hi, yeah, thank you, Tim, and super excited to be here as well. It's always a pleasure to work with everyone here, and we're very excited about this opportunity. at Fast Radius. And Fast Radius really is a full solutions manufacturer. We work in many different industries with companies large and small. And at Fast Radius, I work on our application design and development team. We work with customers to help them develop applications, whether it be from a simple sketch, an idea, or if it's a more developed idea or product, and we help them identify where additive manufacturing can help them get that product to market. So again, very excited to talk about this new material, and I'm happy to be here.
Great, Alex. Okay, let's advance to the first slide, if you would, please. Yeah, maybe the one beyond this. Yeah, perfect. So maybe just a quick preamble. I think you've heard from myself and all four of us panelists that this is an exciting material. I'm a sort of a material scientist background technologist, and so I tend to get excited by this type of stuff. I guess that's why I'm in my role, but I hope you get the sense of excitement. This is something new to the market, and I think it's really going to fit the niche that Jesse was talking about. And today we'll be there to answer all your questions along those lines. Let's move to the next slide. I want to talk about at least the value proposition as we see it, and it's kind of up here, on the screen. The first is performance, and there's probably three aspects of this, right? The first being performance. One is it's got really good rebound resilience. We'll probably talk about this more as we get into the applications, but as you start talking about lattices, the ability for it to rebound is actually something that's really critical when you look at the energy return for a lot of these different type of lattice and sports, different applications. So that's one. It's also lower density, right? Which is also very important for sports. If you're getting into something, and it's going to be sitting on your head, the lighter is better, right? Later on, Rebecca's going to show a cool slide of a ice climber, and it happens that that's my hobby in my spare time. Maybe not this year with COVID, but I like to get out. And so not only is it lighter on my head and have that performance, it's also low temperature resistance, right? So something very near and dear to my heart, which is something that's going to protect my head when I'm out in the cold, right? So that's the first one, is the overall performance as a material that we're basically bringing to the market. The next one is it's based on a polyamide. The additive manufacturing world's very familiar with the different polyamides that are out there, PA12, say in particular, and has years of experience with that. And Rebecca's going to discuss this more, of course, but it basically brings those attributes that those of you who've been working with polyamides are used to, right? Which is different than maybe some of the existing elastomers that are out there. One, it brings good quality, good surface finish, a good look and feel, good detail, and by quality I mean having isotropic material properties that allows you to do different things, not even just prototyping, and potentially actually real world implementations as well. And of course, it can be chemically polished. I've got one part here. I apologize maybe for my lighting here. But if you're trying to get the right look and feel, this material, like other polyamides, is also capable of being polished as well. So the first value prop, performance of an elastomer. The second one is a material that most folks are familiar with if they've been dealing with polyamides. The third one, which kind of builds on that, is it's a very, is the workflow. Right, and so it actually cleans up much better than a lot of the existing elastomers that are out there. So if you're creating a lattice structure, such as this helmet, and you're trying to get the powder out or clean it up, it lends itself to that quite well, and is not nearly as sticky as some of the other elastomers. Right, so that's kind of the overall performance value proposition relative to those three things. And if you have questions, as we get into it, that you want to dive in a little, click down a little bit more, again, please put them into your chat screen. All right, let's jump to the next slide, please. So from an application standpoint, we see three, right? One is kind of, not kind of, industrial, right? So end of arm tooling. Actually, the part that you can see on the screen here is the part that I'm holding up. See if I can get some light on it, where maybe you need soft grippers or what have you. That's one application. Another one might be just such as this, tubing part here, which needs to be some flexible. You need to be able to attach it onto, another part along those lines. So clearly from an industrial standpoint. I talked about sports equipment, in particular helmets, and I've shown this helmet already. And I also talked about, winter gear, and we'll dive that into a little bit more because it's low temperature resilience. And then the third one is automotive. I've got an interior part that's been chemically polished. It's got a fine texture to it. I'm going to hold it up here and see if you can't quite see it here. But if you're basically prototyping for some automotive application, I mean, this part is really nice, right, from a surface finish standpoint and the ability to kind of prototype for that. And I think Alex and Jesse will probably get into at least their perspective of that as well. So at that point, let's jump to the next slide, and I'll kick it over to Rebecca to talk about Evonik's perspective.
Thanks, Tim. So the first thing I want to do is maybe bore you of 2 minutes of our background. Since we are a B2B company typically, a lot of you don't know us. So just to let you know where we've come from. So we are one of the world's leading specialty chemical companies. We're based in Essen, Germany. We have turnover about 15 billion. We're active in over 100 countries, and we have over 32,000 employees, just to give you an idea of scope. Leading beyond chemistry, we work toward a common purpose of improving life now and in the future. We're made up of 4 main segments. We have specialty additives, where small input makes a big effect. We have nutrition and care, and that group provides materials that revolve around health and quality of life. Performance materials, where we have our classical technologies that we try to continuously improve. And my favorite, where I come from, smart materials, where we're proud to offer high performance materials that pave the way to greater resource efficiency and sustainability. We have specialty composites, we have specialty membranes, high-end lightweight foams, as well as ready-to-use material into additive manufacturing. And since a lot of you may not know our name, please trust me, we have been setting quality standards for 20 years, leading development and manufacturing of customized powders or polymer materials for 3D printing. And we're now looking forward to demonstrating our capabilities with end users through this new specialty elastomer. You can go to the next slide. So now to talk about the chemistry, as Tim mentioned, it is a material based on a polyamide. This particular TPA is a block copolymer consisting of hard segments, which are PA12, and soft segments, which are made from polyether. So the polyamide hard segments give it the high chemical resistance and the high abrasion resistance, whereas the polyether soft segments give you the high impact strength at cold temperatures and make it very flexible. So the major properties you get out of this block copolymer are low density, as Tim has mentioned, high energy return, high elasticity, and good resilience, impact strength and consistent properties across temperature gradients, which impact strength, I know any of us that are dealing with anyone in the automotive field, that is really a key word right now. We need more impact strength. And then also we have a broad processing window so that you can have a similar experience to when you're printing PA12. And I hope that Jesse and Alex can tell you about their experience as well. You can go to the next slide. So as Tim mentioned, we would probably be talking about some of the same concepts over and over. And this is really something that I'm a true believer in. It's educate, reemphasize, reemphasize. And with this material, it really needs to be done because it's not a brand new chemistry in the market, but it's a high performance chemistry that is now gaining traction. It can be foamed, it can be molded, it can be extruded, and now it can be 3D printed. And just to talk a little more, we say it's low density. Low density means lightweight. We are typically about 20% lighter than competing elastomers. So what that means, you pretend we have this part. Let's just say it weighs 10 pounds. Obviously it doesn't. It weighs 10 pounds in maybe a TPU, copolyester, some other elastomer. It's 20% lighter, so it means this part weighs 8 pounds when it's made out of the TPA. So same geometry, same part size, same density of the part. So we're not trying to say that the part is porous when we say density. We're saying the actual material is lighter. The second component, the high energy return. This is another one that I think sometimes people get confused over. There's energy return, there's energy damping, there's a time and a place for all materials, and I want to make sure that people understand what we mean by high energy return. Think of a super ball that you're bouncing on your desk and it's returning. We're not saying that it returns more energy than you put in it, but we're saying it has very high energy returns. So it gets higher to that starting point than many other elastomers in that market. So we're seeing that terminology, I think, in footwear right now with the Marathon, the new Alpha Fly shoes, energy return, energy efficiency. That's all what we're talking about right here. And then the third point, I'm glad to know Tim's hobby. We're going to have to make him a helmet. Consistent properties at low temperatures. So there's two things that are contributing to this. One is that we're not using any plasticizers in this material. It's made out of the soft and hard components. So when you get to a hot temperature or a cold temperature, you're not having any kind of plasticizer extrude out of the material or exude out of the material. So you remain pretty consistent. You also have a low T sub G, which allows it to have that impact strength at -30°C. And we find among the popular elastomers, this is one of the most consistent products. Yeah, it'll get a little harder, it'll get a little more brittle at those cold temperatures, but it's pretty consistent when you take it compared to what's available in the market today. So I think that's all I had, and I'll turn it back to Tim. I hope we can hear some great stories of how Alex and Jesse see this material process, as well as how they're able to take advantage of some of these characteristics.
Great, Rebecca. That's awesome. And let me ask the first question to both Jesse and Alex. And remember, the audience out there, please ask questions into your chat, because as soon as we're done with this question, my expectation is that we'll be able to, dive into all of your questions that you might have on any aspect of it to any one of us, right? But the question, I sort of teed it up at the beginning with Jesse and Alex, is tell me about your overall impression of this material, just kind of what it looks like, what applications you think that's lending, or what applications you've already developed for your customers, then maybe a little bit about this development model, because I think that's something that's key from my perspective, is to be very, very customer focused on these applications as we develop future materials. So I'd be just interested in your take on that. Jesse, let's start with you.
Thank you, Tim. Appreciate it a lot. And really both you and Rebecca have given some great information so far. So I'll just try to kind of feed off of that. So Go Proto is a fulfillment company. We manufacture parts from 3D printing machines and conventional machines that are made by other companies, and then with materials that are sourced, either specified by our customers or something that we have researched and found is a great material that we can use to address customer needs. And so as we've looked around, I've been in the industry since the mid-90s, and ever since essentially the commercial introduction of 3D printing. And all through the course of that, there's been some really awesome rigid materials, but there really hasn't been an elastomer material that has worked very well. Selective laser sintering process has had a couple of elastomers that have worked okay, but they're kind of grainy and they don't have a lot of good isometric or isotropic properties. They tend to split in the Z. FDM has got some issues with the same sort of thing. Production grade material, but because you have incomplete bonding between the layers, you end up with parts that potentially split. They've also got issues with supports and things that make it kind of only applicable to a certain little narrow swath of what might be needed from customers. Then I mentioned injection molding, or cast urethane, excuse me, where you make a master pattern silicone rubber tool off of that master pattern and then cast multiples into the tool. And it's got some great capabilities, but it's a thermoset urethane material that's simulating a injection molded or compression molded elastomer. So only good in certain applications. Certainly can't go low temperature like Rebecca mentioned, or high temperatures if you're going to be putting it in automotive. So there's limitations there. Also limitations on geometry and cosmetic genetics and chemical exposure, you know, lots of different things. Also, over time, the material will change. It starts out nice and rubbery, and then it gets brittle over time. And then we get into injection molding or compression molding that require tooling and certainly have limitations on the types of geometries that can be made. So, and also, of course, it's just expensive to make a tool. So you're going to only really want to get into that when you start to have quantities that justify it. So there's been this big need in the market, and we've been looking at it for years and years. And when this material came out, actually, I mean, we've been looking at the other multi-jet fusion materials as well. You know, there's the TPU materials, and those are interesting, but there are some limitations with those as well. We run the material, we've used it, but they're a little on the higher end of durometer. They're more like 95. There's also some processing things with it, and some other limitations that make it, you know, a little bit narrower applications. Then when you look at the TPA material, it's got a lot of those limitations are removed. And so we as a fulfillment company helping to address customer needs have been really excited about what this can do for real practical applications. So so there's that side, plus then the processing side. How does it run on the machine? So, you know, we don't want to have to buy a bunch of more equipment, take a bunch more time, make it really expensive for customers. It needs to really be something that we can run through our normal workflow. And that's a really exciting part of it, because it actually processes quite similar, because it's polyamide based, processes quite similar to the PA12, which is kind of the workhorse material that we've been running. So we've tested it. We've been involved with the testing of this material since about, I think, April or so of 2020, and we've run, you know, hundreds of builds. We've run thousands of parts and find a very consistent workflow with it. And that means that from a customer's perspective, you're going to get dependable deliveries, you're going to get dependable quality, and we can the pricing is really quite similar to some of the other materials. So lots of opportunity there. Hopefully that answered your question, Tim.
Yeah, that's great. Maybe talk a little bit more. You mentioned production a couple times.
Oh, yes.
Typically, we think of additive manufacturing be, you know, lots of times prototyping. But at least from the HP perspective, we see more and more production applications. What do you think about this material relative to production opportunities?
That is a great question. Great point. So as Rebecca mentioned, this basic chemistry can be made in injection molding materials. It can be made in, you know, many of the conventional processes for making production parts. And this is just essentially a powdered form that can be 3D printed. So when you look at it as a customer, a lot of times, or as a designer, let's say, or a product developer, you often have to make a compromise for your prototype kinds of parts. I mentioned before that you might make it in the past from a photopolymer, like a carbon or a stereolithography material, or DLP material, and those have got compromises. They won't do certain things that your production material will. So you always have to have this kind of like, well, if it was the production material, it wouldn't have just fallen apart as I tested it, or dissolved in that chemical. So you have this kind of production or prototype mentality while you're testing the part. But if you could test it in a material that is a production type material, then, or production material itself, then you know that you can use it just like you're going to for your production part. That might mean that you only do it for 1 part, 5, 10, 20, kind of low quantity, or you may realize, you know, this is working just great in all of my uses. And so I may not have to go to the production process. I may not have to make an injection mold or a compression mold to manufacture this part. I could just print, you know, continually, essentially from here on out. And that means you don't have tooling costs. You might be able to, say, make design changes quickly with no additional costs. There's a huge bunch of possibilities that unlocks. And then if you do go into injection molding, which we offer, I know Fast Radius does too, you can realistically jump right into this very similar material or the same material, just compounded differently, that you can make production parts with. So there isn't a big bunch of learning curve like, okay, now we're going to switch out of urethane and go into the TPA material. You're going to be running the TPA the whole time. So from the production prototype through production continuum becomes much less big step, giant leap of faith, you know, bunch of risk involved. You know, the idea is to minimize risk here. And that's what this material does in a tremendous way. Great.
Thanks, Jesse. Let's jump to the next slide, and the same question to Alex around your general impression of the material, the applications that you're developing, or the applications your customers are developing, and any comments you might have on the development process of getting this material out jointly with the four teams here.
Yeah, certainly. Thank you for that. So when I think of TPA and our experiences that we've had with it, one of the things that really pops out to me is it's really the combination of the MJF platform plus the material. And Jesse alluded to this a little bit when he was talking there, but there is this ability now to print things that you couldn't print before. And it really unlocks some really, really cool things that you can do here. And like you're seeing on the videos on the screen right now, you can do fabrics and textiles in these really, really cool patterns that, really are challenging to print in any other way. And it unlocks this new freedom of design. Having my background in product design, it's something that I'm always thinking about. How can we create and unlock these new things that we haven't thought of in the past, or there's been so many limitations that it's just not made it feasible. And so we're so excited about this material and being on the MJF platform because it's started to unlock a lot of those things. We have a really, really creative design staff at Fast Radius, and we come up with some of the wildest ideas. And this technology has enabled us to begin to print and do a lot more of them. A really cool example of that, what you see in the back of that screen, and I'll have it here. You can see it up on the screen itself. But we've actually created and printed a full shoe. Granted, this is for like a kid, but we've printed a full shoe where we've actually integrated a textile on the top that stretches and bends and would feel very, very comfortable on your foot. And we've also then integrated also, the unique conforming lattice design on the bottom. Things like this you couldn't do out of one material in the past, and now it's starting to unlock that. And so we're really, really excited about that. When it comes to applications in general, I mean, I think, we've been working with a lot of different customers in a lot of different industries, trying to help identify applications. Automotive is a big one, sporting goods, industrial, and countless others. And I think like this material certainly has its place. It might be one of the best in the industry because it, again, unlocks a lot of potential that you can't use and you can't do in these other technologies. We do a lot of lattice design work like I was just showing you. And with some of the other technologies that we use internally, it's been a very big burden to always have to think about, all right, how is this going to be on a platform? How is this going to be supported? Is it going to fail? How is it going to fail? Well, with this geometry, I mean, there are still rules that you have to follow, like anything, but those rules are less severe and easier and have really opened up, allowing more and more applications to be designed and developed. So we're really excited about that. I mean, there's just a lot of opportunity out there and we're very confident in. And then as far as process goes, when I talk to our operations folks at Fast Radius, I mean, first and foremost, we pride ourselves on developing robust processes similar to what you would see in high volume manufacturing, like injection molding and CNC, and so on and so forth. And we have done the same thing with our PA12 operation for MJF. And what has been very surprising and honestly very exciting is that we can take this material and throw it into that same process and have very little change. We don't need to develop a whole new process. And that saves a ton of time, a ton of resource hours on our end. And it also brings in, to Jesse's point, confidence with our customer base that this is going to be a robust material that fills their needs. So we're very, very excited about it.
Yeah, cool. Thanks, Alex. And it is exciting. There's a number of questions now in from our audience. I'm going to juggle them around because the first one's kind of building off of what you were talking about, Alex, which is what was the micron thickness of the fabric, or how thick or how thin can you go, and then basically how far can you stretch it? Right? What is the what is the elongation that we can basically get that? And that might be a question to you, Rebecca, as well. Maybe say a few words, Alex.
Yeah, I can start there, and I'll should certainly let Rebecca answer the more specific elongation to the material. But when we were developing these fabrics, I believe the thickness, the beam thickness that we have in this is around 1 millimeter. And this isn't to say that we've designed encompass the full breadth either. This is more of just like a beginning kind of experiment to see where things turn out. So there's a lot of work, a lot of design freedom that could really go further here. But it's around 1 millimeter, and then the gapping between was anywhere between, I believe is like 0.3 millimeters of, or sorry, 0.25 millimeters of spacing. So there's freedom there. There's a lot more to really dive into there.
Yeah, I would, this is Jesse, I would echo that same thing. This is a 3D printing process, and as such, it has kind of some of the similar, just like say injection molding has some of the design concepts that you need to have. 3D printing has the same thing, and as Alex just said, generally around 1 millimeter or 40 thousandths is you're for sure going to get features that print well or walls that print well. If you go lower than that, the printer can do it, but it's a little less predictable. Sometimes it comes out well, sometimes it doesn't, sometimes it warps, sometimes it doesn't. There's things like that that can kind of come into play. We've been really impressed. That is something that comes up with elastomers. We've been really impressed. I've got a little part here that's a little simple strain relief, and it's very thin walled. It's about probably 1 millimeter the whole wall, and there's a little video delay, so I'll try to kind of show it. But you can bend it around, even at 1 millimeter. It'll do these amazing flexing that you hope that a part that you design can do. A lot of times, if you're making a thin wall and you 3D print it in the carbon technology or the object technology, you're going to get a break. It's going to break in all kinds of different directions. And again, as a service bureau, I'll also say the same thing. It's a tragedy. It's a big bummer to ship parts to customers. They try them, they're like, they broke real quickly. And so it's nice to be able to say print parts that are thin and still perform very well. So that's important on the thin. So you mentioned the thickness of the material, then also the spacing between the components. This is a powder bed technology. So there's not supports to remove like there are with FDM or stereolithography or even DLP. There's powder to remove from the part. And so that means you can do things like trapped volumes. This is a bellows part that has got a hole on the top and a hole on the bottom, and it's hollow in the middle. So we had to get the powder out of there, but there aren't supports to try to figure out how we're going to get a little tool in there and remove it. We can shake it out, compress it, put it through our vibratory deburr, and it's gonna remove that powder. So that frees up a lot of shapes, as well as, like Alex showed, lattices and features that are going to have some trapped volume. You can get the powder out of there really, really well. So does that answer that?
I think that's a great answer.
And I have another thing.
Yep, go ahead,
thin
Rebecca.
chart
Yep.
to show, and again, I would default to you guys to talk about really what's realistic in applications for wall thickness, because you're really the experts on how to push a material beyond how we sometimes believe it can be pushed. But I was impressed by this very thin walled part that I got from our lab. It actually arrived to me, I don't know if you can see, dented like that, and I thought, oh no, what happened? And it just pops out and it's fine. So I think this is definitely under the millimeter, but it did work.
Yes, that's a very good point. Also, I would say I've got a sample part here that's a test part that HP, being a very smart company, understanding that they need to develop some well-engineered solutions, does a lot of testing. Right. That's one of the reasons we, as a small service bureau, jumped into partnership with them, because we know that we can exercise the use of their tremendous R&D, and same with Evonik. And so they do things like test the heck out of different parts like customers might use. And this is a good example of their test part that's got a big, thick, solid cylinder on one end, a slightly thinner one, a bunch of smaller ones, and then walls that connect to make sure that the things print well and get good dimensional accuracy and don't have a big bunch of cosmetic defects. This part has been post-processed smoothed, so that affects the cosmetics, but you can see that it came out excellently. There in the last question, Tim, you did mention elongation, which I wanted to address a little bit, get into the specifics. We found that this material can stretch somewhere between 200 to 400%, depending on design features, depending on build orientation, there is a little bit of non-isotropy to it. It's a little bit weaker in the Z than it is in the X and Y. It also has a lot to do with the post-process finishing, which I want to address. This material can be vapor polished post-process, so we put it in a machine that exposes it to vapor that is a solvent that kind of reorders the molecules on the surface, makes it look nicer, also improves the elongation. So you can get parts like I'm holding up here that will stretch and return to shape. They can be twisted around. It really improves that non-isotropic process and improves the elongation, which means it improves the impact strength, it improves the elasticity. It also improves the water resistance because it locks the surface, and also to some degree some chemical resistance. So there's some things that the basic material is awesome, the process is great, and then there are things that you can do to improve it after that can make it even better.
That's great, all three of you. Thanks for that explanation and detail. So we talked a little, there's now some questions here, so we're going to dive into some of them. So we talked about chemical processing as one potential way, but what are some of the other ones? One of the questions is, can you color this material? And anybody who's familiar with our 4200 and materials know that we can print any color you want as long as it's sort of dark gray. But maybe talk a little bit about some of the other different things you could do as far as, coatings or colorings or plating to bring color, and any experience you might have along those lines.
Yeah, you bet. Alex, do you want to talk about that, or you want me to, or Rebecca? We can all three kind of jump in there.
Yeah, I can start real quick. So at Fast Radius, what we have experience with this material in particular is dyeing the parts. I don't have one here to show you, but I'm sure what you've seen so far, it will just look like a black part. But that actually seems to work very, very well. Very similar to what Jesse has on the screen. Works and very similar to like the PA12 part. So if you've received an MJF PA12 part or PA11 part in the past that's been dyed black, it will look the exact same. But that is the main process that we have had experience with this material.
Yep. Yeah, I would say this is a large orthotic boot that is good to show just because it's big enough that you can see the surface finish. When it's just tumbled, it's the same kind of matte gray finish. And then when you dye it, it turns it black. We also have dye, Alex, you guys have probably tried also different colors. We've tried it since it's gray, dark gray to start with. You can't do light colors really. It's not set up for white yet, which is a question. It's not yet set up for light yellows and those kinds of colors. It can do darker colors like dark blue, dark red. We've also done dark green. So it can do those. I don't have those right in front of me here, but primarily it's black. Then when you smooth it, it does become darker, more even black, or it'll lock in. If you have blue or green or red, it'll make it a darker color. Sometimes it's kind of hard to tell that it's not black. So there's not a huge range of color options at this point that are in the print or in the dye. The next options are to possibly dye the parts. There's another process that we haven't really fully investigated yet. This is still a fairly new material, but some dyeing that can be done. Also some post-op painting that can be done with materials that'll bond to this. So just like it's polyamide based, and there are paints that will adhere to polyamide. It's the same thing. We'll be able to paint it with materials that are soft touch that'll grip onto it. That'll give those cosmetic colors.
Yeah, perfect.
And from
Thanks,
our
Alex.
side,
Thanks, Jesse. Yep, go ahead,
Sure.
Rebecca.
Yeah. So we didn't really look at dyeing too much, but one of the hurdles when I was kind of showing everyone these parts and seeing what the market interest was, a lot of the issues with elastomers were that people were complaining about the unpacking process and getting the powder out. And even when you get the powder out, you're still seeing little droplets every once in a while. Tim, your predecessor, used to complain about, why is there always powder on my desk after I have a part? So I knew we needed to find a solution. And everyone I went to for basic tumbling said, no, it'll never work. It's an elastomer, you can't tumble it. So we started searching for other methods, and that's when we started investigating the smoothing. And it did two things. One, because we're not selling parts, I thought, wow, I can smooth it and it makes it black. I don't even need to dye it. I'm sure by a service bureau's what they would think is, no, that's still not good enough. But for me, it looked very black. At the same time, it makes it look like it's an injection molded part, basically. It's got kind of that nice surface finish. It completely seals it, like Jesse says. If you can see, sorry for putting it in front of my head. If I let go, sorry, there's a delay, but yeah, it can get good tightness,
Sealing.
air, water tightness. Yeah, and another thing we did, people were complaining they didn't want to look at the elastomer because of the unpacking experience. So I ended up making a bunch of these, or not me myself, but I had an engineer print a bucket of these. We didn't take any powder out of them. We put them in a bag. And anyone that knows about being on a chemical site, getting anything shipped out takes longer than it should. So 2 weeks later, these arrived at a service bureau. We said, hey, can you just run it through your PowerShot C or whatever depowder you have? And they said, oh yeah, one 20-minute cycle, it's depowdered, no problem. It was easy. You had some really tiny, some parts with really tight circles, and we ran that for 1.5 cycles, and everything was fine. And so that was really exciting for us, because now we're starting to find ways over the main objections of why people don't like to work with elastomers.
Yeah, great. Thanks, everybody. Let's jump to another question that's come in, and this one's maybe one for you, Rebecca, although Jesse was touching on it as well, which is, if you wanted to adhere something to this, from an adhesive or what have you, what type of adhesives would you recommend, or is it similar to what you would use with PA12?
Yeah, that's something we may have to go offline on. We're just kind of starting this process, and the good news is we have found some adhesives that do work. There haven't been any major issues. Like I said, we're just in that playing part, and I think Jesse and Alex have some experience as well. But we are able to bond it, which is great. So yeah, if I could turn it over to Jesse for his experience.
Sure. Yeah, we've specifically had a couple of customers that have had that issue. One, because they wanted to the way that they were going to make their assembly had some adhesion that they wanted to do, and then also the printer is limited. I often forget the exact dimensions, but it's 11.2 inches by 14.2 inches by 11.2 inches tall. So if you have an automotive duct that's larger than that, then you're going to need to print it in sections and either mechanically bond it. So like, say you could print it in a section that's folded over and then fold back together and it'll snap together, or you're going to need to bond it. So that does come up from time to time with our clients. We do have a 3M adhesive that bonds the material extremely well, and it will then hold. It also will allow for that elasticity to continue. So it's not like you're bonding it with cyanoacrylate that's rigid, that's going to break as soon as you pop it, as soon as you try to stretch it. So that's a huge obstacle to overcome, but we're very excited about that.
Great. Thanks, Rebecca and Jesse. Let's jump to another one. And Rebecca, I think this one's for you as well. Is the material UV stable, right? Does it work for outdoor usage?
It's not specifically stabilized. So for this specific one, we can get you a UV stabled one. I'll just need you to help me get Tim to get priority to push it through the system.
Yeah, fair enough.
Same with the color. But yeah, it doesn't have extraordinary UV on this grade.
Yeah, so maybe then the next question goes to Jesse and Alex, back to sort of, coatings and so forth. Any experience using UV protective coatings with this material, or what are your thoughts there? Alex?
Well, yeah, go ahead, Alex.
Oh, yeah. So, I mean, UV, I think with pretty much all additive manufacturing materials is typically a problem to some degree or another. And so what we found in the past is, if there's an application that we've come across that requires a high level of UV stability, then we will source some type of clear coat. Now, this being an elastomer, it needs to be similar to what we were just talking about. It needs to be a coating that still has the same level of modulus and elasticity, so that it doesn't flake off over on like excessive wear. Think about like a lattice, and you coat this, it has to stay on throughout the life of the product. And so you need special coatings to do that. This specific product is something that we're still working through on what that would be, but I'm sure there is something out in the marketplace today for that.
Yeah, okay.
And
Yeah,
just to
I'll kind of
emphasize,
Jesse
sorry,
and then Rebecca.
just quick, Jesse.
Yep.
The chemistry can be stabilized. It's just that when the product was being put together, you know, unfortunately, this is it just didn't make it in the top items when it was going through the process. And because, you know, HP has this great process where you just have to press start and your print goes, it means that any change to the formulation means it has to go through a lot of testing at HP. So the chemistry is able to be stable. The injection molding grades we do have heat and light stable. It's just that this actual particular one is not. It is something that we can do. We would just have to see, if it would make any significant changes in how it's being printed.
Fair enough.
I would
thought.
Sure, yeah, definitely. I'm not sure whether the question is about cosmetics, like does it fade, or if it's more about mechanical properties, if that tends to degrade the mechanical properties. Did they say in that question? I can kind of address both.
There's not detailed in that question.
Okay, all right. So let's talk about cosmetics, I guess, first. Is it going to fade? You know, when we're dyeing these with the basic material here is gray, it's really not going to fade much. It's not going to, if you expose this to sun or have it in an office where it's under ultraviolet light for a long time or under fluorescent light, it's not going to really change much. Certainly way the heck less than any of the photopolymers that we've worked with in the past. If you're using any DLP material, those are state change materials that go from liquid to solid because of exposure to ultraviolet light. So when they're done and they're cured and you're using them, they are still curing, and that's why they become more brittle or yellow, or they might sag over time, whereas this material won't do that. It's way more stable in the basic environment. We haven't tested it in a UV chamber over hundreds of hours and so on, but I'm pretty sure it's going to stay pretty similar. It might change just a little bit. Then the other thing is that we dye. You know, Alex has talked about this. I've talked about it. We dye it with RIT dye, fabric dye, which is quite stable under UV. Again, we haven't tested it for color fade, but it's pretty darn stable. This is going to be way better than really anything else that's out on the market. So I know that's kind of a general answer, but it is, you know, knowing what we know from what customers are driving for, it's like, this is so much better than anything else that's out there, that the answer is it's going to be a heck of a lot more UV stable than most any other 3D printed material you've seen so far.
No, that's perfect. Thanks for the answer from all three of you. Let's jump to another one, and maybe start with Alex and Jesse, then we'll go to Rebecca. But have you seen any medical applications that utilize this material? And I would say, so let's start with this, but maybe there's ones, Rebecca, that are currently used in injection molding, where back to the earlier conversation, you could start to prototype with this material. But Alex, let's go with you first.
Yeah, actually, Jesse, if you could hold up that part again, because the main one that we've seen and come across our desk as well is, you know, boots and stuff like that for prosthetics. But yeah, exactly. I don't have one of those here, unfortunately. But that is a very, very good use case for the medical. And that's all I have in particular, but I'm sure there's more. Jesse, I'm sure you can elaborate more on that.
Yeah, yes, certainly. We do a lot of med device work also. So this is a great process. 3D printing is exciting for things that fit on the human body, because the human body varies by every single person, and often right and left on one person are different. So customizing things like shoe soles and things that are orthotics, you know, that are going to say help someone's step, or like I showed earlier, this is a replacement part. You know, we've focused a lot on issues with corrective devices like walking aids and robotic hands and things like that. That it's got tremendous application with that. There's also the med device side of things, like, you know, you've got an articulating arm that's going to have a boot or something that's going over the wiring, and we do a lot of that kind of work. So almost more on the robotics side of medical, and that's a big application. We've done a whole lot of that. Also, because as you mentioned before, Rebecca, and you've mentioned it too, Tim, that molecularly this stuff is lighter weight. It's good for things like hands and helmets and things that are fitting on the human body, and that you know, you don't want to tire someone out. Or also robotics, things that are going to be starting and stopping quickly or need high precision. Like I just mentioned, robotics for medical, having lightweight is important. Of the the molecule, and then also just the structure. You know, the fact that you can make lattices that are going to lightweight something, tremendous applications for this kind of feature in medical.
Rebecca, any closing thoughts to that question?
Yeah, just to mention that traditionally this chemistry is actually a big product for us in the medical field. What we normally use it is for catheter tubing. Now, unfortunately, with this product, it would not pass the levels of regulation needed to be in-body catheter tubing. However, similar to what Jesse's saying, a lot in orthotics and prosthetics. And I guess our fear at first was, can we go after these if we don't have, you know, a class 6 for this particular product? And everyone's feedback for the most part seems to be they have covers on them anyway, so it's actually okay to go after. So as long as you have a fabric or a cover or something over the part, then it's great for things like that, for helmets, for orthotics, for prosthetics. Yeah, those are a lot of what we're seeing as well.
All right, thanks, Rebecca, Jesse, Alex. There's another set of questions here, and we've touched collectively on this a little bit, but there's a couple questions. I'm going to kind of combine them together. Advantages of TPA versus the TPU you've used, and also specifically a number of the questions people have used the existing TPUs available for MJF. And what do you see as, you know, the differences, maybe just to be very explicit, the differences and advantages with this material? Let's start with Alex, you again.
Yeah, thank you. So some of the clear advantages we've briefly talked about the material itself, and some of the advantages there: lightweight, it has higher or better elongation at cold temperatures. Energy return is a big one as well. But when you think about the process, and that's the thing that, you know, we have an elaborate onboarding process for any type of new material. I'm at Fast Radius, and one of the things that we always look at is like how stable is the process itself to produce and use that material? How much change is it to go from our standard process? And so with this material TPA and comparing that to the TPU materials, we found that TPA is because as a polyamide, it's very similar to PA12. It follows the same process very, very smoothly. You know, I think the only thing that we've noticed a difference is because it's an elastomer, when you go to post-process it, it does take a little bit more time, in particular if it's like a lattice type geometry for like tumbling and cleaning some of the powder out. But besides that, the actual printing process, and for the most part, the post-processing and dyeing can be very, very similar, if not identical. And so that's been a big thing for our side of Fast Radius, is how well can we translate from going our standard PA12 process to a TPA process, and then how does that compare to TPU? It's just smoother, it's faster, it's easier. We've also seen that with the TPA, it's a more precise material. And so we've been able to get a little bit better dimensional. Now that may vary and does vary on the parts that you're printing, where they are in the build volume. But we've seen some pretty good results, repeatability, variation control with the TPA. Yeah,
perfect. Jesse, any thoughts?
Yeah, I would agree with all those things. Great points, Alex. And I would also just say that the material is a little softer. It feels better, it performs better than the TPUs from what we've seen overall. It also vapor smooths, as I mentioned earlier, which is important for cosmetics and elongation. Also, water absorption. Once you smooth it, the water will bead up on it. It doesn't go through the material. So that's important because a lot of our customers are looking for grips and things that are going to take pneumatic or liquid pressure, and so they need to be able to seal. And so that was real important for us. As Alex mentioned, the processability, fairly low cost, similar to the rest, was important. Availability of material, a huge part of it is the development mentality that Evonik has, you know, like understanding their offerings of their products, and then it's beginning to end offerings. So everything from prototype up through injection molded parts is very important. We needed to know that we can jump in and have a tried and true path. So that was important to us. And again, just that the material performs well. It feels great. So that was one of our major selection criteria.
Yeah, cool. Rebecca, any thoughts?
Yeah, I kind of have a question for Jesse and Alex. I don't know if they can answer this, but time to part. I believe that the time to part's kind of important. You're a service bureau, you're a business, you're trying to get things out the door, start a new build. It's 13 hours is what we get for a full build. I try and be a little bit agnostic. Every material has a time and a place. So we already touched on the lighter, the energy return, but time to part. What do you guys see?
Yeah, it's similar to what, like Alex said, it's similar to what we see with other processes. Generally with multi-jet fusion, it's a thermal process, so it has to heat up, build, and then cool down. And so we generally quote 2 to 3 days, sometimes longer than that if it's a long build, but it's the same sort of lead time, rapid prototype to quick delivery, fast, and it can be that way repeatedly. So as you decide we need to make 1,000 of these things, and it's going to be 5 builds worth, that we'll be able to repeat that performance build after build after build. It's quick.
And I would echo the same thing. We see that this material prints very well, and it's very similar to the PA12. We love that we can do a full build volume with this material, whereas some of the others, there's issues with dimensional stability the higher you get up in it, growing the Z height of your build volume. So there's a lot of advantages to the TPA. And I'd say, again, like just being able to follow the same PA12 process has been very enabling for this material to be onboarded much, much faster than if it, is a process that is very drastically different. So.
Yeah, awesome. And thanks for that question, Rebecca. Hey, we've got about 4 minutes left. So here's what I'd like to do. Maybe to let each of you have a few seconds, just any closing comments or things that myself or the audience should have asked, or your thoughts around TPA, and then I'll close it up for ourselves and the audience. Rebecca, let's start with you.
Yeah. I guess I would just like to thank everyone for tuning in. I would love to engage with anyone to talk about anything we can do to help you better understand the material. Thank Jesse, Alex, and you, Tim. As I said, HP, Go Proto, Fast Radius have been incredible partners. This has been a really great process. I really love this development style, and that now we can really talk about the fruits of our labor. So thank you very much, and thank you all for attending.
Yeah, great. Jesse?
Great. I would say the same thing. This panel is actually a really interesting point. We've got HP, a huge manufacturer of machines and some materials and everything, massive R&D capability, and certainly understands manufacturing. And then you've got Evonik, this massive company that's an incredible chemical development company. And then you've got 2 service bureaus that are delivering parts here. This shows this partnership here that if I were a client or customer or product designer listening to this, I know that I've got that kind of horsepower. And we've seen that already. Some companies developing footwear, some companies developing helmets and things that they're like, hey, I need, like someone asked about the UV stability and all that, I need to talk about the material and maybe some development that can be done with it. And seeing that this kind of group is together to help truly develop and move this thing, say, into Industry 4.0, where you can use 3D printing for your production process, is why we are so excited about this. This isn't just another material that's kind of cool that can do some things. This is truly a groundbreaking combination of incredible technology, incredible machine to print it on, and then service bureaus that are set up and ready that are able to develop and deliver on low to quite high volumes using additive manufacturing. And this is a game changer. It's definitely different.
Yep. Agree. Alex?
Yeah, thank you. And I mean, I said it all, but we're excited. Thank you for being on this panel. It was great to connect with everyone. And if anyone's listening, has questions and wants to talk about lattice design, talk about fabrics, talk about any of the different applications out there, feel free to reach out to any one of us. But this has just been a great pleasure, and we're very excited about this material and the relationship that we've had with everyone on the panel. This has been fantastic, guys.
Yeah. So first and foremost, I'd like to thank everybody who's listening and echo what everybody said. Alex, what Alex was mentioning, if you have questions, contact any one of us and we can dive in deeper. But Rebecca, Jesse, Alex, I appreciate you taking the time out of your busy day to be here on this panel and talk about this exciting new material, and maybe more importantly, the exciting applications. I want to build on what, and then more than that, the fact that our companies did work together to get this out, and the model, which is the fact that for future applications, say we had a customer, a big application who wanted to develop, a UV material, with this or some other thing. This is the model that we're taking on, where we have groups exactly like this. We want to be focused on the customer applications. We will be focused, and we'll work with all of our partners to basically do that. And so this collaboration that our 4 companies had, I think, is spot on. And I thank you for that as well. At the end of the day, if there's one thing for the audience to take away from this, is that this is an awesome material, right? I hope you get the sense of excitement from all 4 of us. I think there are many applications that exist, and that are that future customers are basically going to find. So I appreciate everybody's participation, especially those that are listening at this particular point. I'll wish you all again a happy Friday and all the best.
Thank you, everyone.
Thank you.